All right. Good day, everybody. My name is Constantine Roros. I'm a senior in computer engineering, and my spin internship comprised of attempting to recognize expressions in movement. So our group as a whole, the goal for this project was to see how computers can recognize gestures and see how that could be applied to, say, music or dance or computer animation. So first we had to figure out a method for interpreting movement. How does one go about doing that? So the first approach we used was Laban movement analysis, and pictured there is Rudolf Laban. And he developed a model for how we could describe the way humans move. And there's 4 components: body, space, shape, and effort. But what we were concerned about were the effort component. And within effort, there's basic effort factors, which can range from indulging, so like a gentle type of movement, or fighting. So this is basically how you approach the movement. So the 4 basic effort factors include flow, weight, so like light movement or strong movement, space. Was the movement aware of its surroundings, or is it just a carefree, lackadaisical type of movement? And time. Was it a sudden movement, or was it sustained? And so we focused in on weight, space, and time because they're more important than flow, and at this stage we were just trying to come up with a model. Eventually we'll incorporate flow, but with those 3, there are 8 possible combinations that form the basic effort actions. So what we did was we recorded data with, in cooperation with the dance department to try and model these basic effort actions. So we tried, a movement that had a strong weight, a sudden time, and a direct space, for example. And so we use that to develop what's called a hidden Markov model, which, to put it in simple terms, is a network of hidden states and the probabilities of transitioning between those states. So we trained the model with this recorded data, these basic effort actions, and we use that to feed in. When we feed in test data, we compute the likelihood that the test recording is one of those basic effort factors. So below I have ROC curves that show the accuracy for weight, space, and time for the different hidden Markov models and how accurate they were at detecting the weight, space, and time correctly. And we had to figure out what parameters from the recordings we used to develop these models, because so for example, you could use position from the accelerometers, or connect, or we could take the derivative and get acceleration, or we could take the dot product between 2 time frames and use that data. And so it was all about figuring out which of these parameters got the most accurate results for the hidden Markov model. So that was the first project I worked on. The second project was how to figure out how to get more accurate, how to derive position from accelerometer data. So it could be pretty useful to get position from accelerometer, since it could be a bit more accurate than, say, a Connect. However, first you need to use a gyroscope sensor to convert the movement into the body frame, because the accelerometer doesn't measure direct movement of a body part. But unfortunately, not everything is ideal, and the accelerometers and the gyroscopes have noise. And when you integrate the acceleration to get position, that noise is amplified a lot. So I've been working on an extended Kalman filter to reduce that error in the gyroscope and the accelerometer, so when you integrate to find the position, that the noise isn't so large. So the extended Kalman filter involved creating a model for the movement of the body. And I compared that to the measurements, and I made an estimate based on that depending on how reliable the measurements were versus the data. And there's the preliminary results. So that's the position if you just take the raw gyroscope and accelerometer data. But there it is on the top. But if you get it from the Kinect, you get what's below. And that's more like what the true movement was. So you can see why we have to develop a filter for that. So yeah, any questions? Yeah?
So your accelerometer data that I see up there, did it match closely what was actually going on?
So that's we take that graph at the top is the raw accelerometer and the raw gyroscope data.
Okay.
So that's with the error. We're still trying to determine how to develop the filter. But
with the error, you mean? I guess I just don't quite understand. Is that that's without filtering that top graph?
Yeah. The filter is still having some issues, like for some reason.
And the bottom graph is?
From the Kinect. Like the position of a body part, the wrist from the Kinect.